Now let's look at the next question. Question number 12, no, 12, 13. Question number 13. Okay, here it is given that a pressure cylinder of volume V contains air at pressure P1 and temperature T1. It is to be filled from a compressed air line maintained at constant pressure Pi and temperature Ti. Show that the temperature of the air in the cylinder after it has been charged to the pressure of the line is given by. So now let's look at the next question, question number 13. In this question, it is given that a pressure cylinder of volume V contains air at pressure P1 and temperature T1. Pressure cylinder at volume V has air at pressure P1 and T1. It is to be filled from a compressed air line maintained at constant pressure Pi and temperature. So it is being filled from a compressed air line, which is at a pressure Pi, Ti. So that the temperature of the air in the cylinder after it has been charged to the pressure of the line is given by. So finally, it will go to some pressure T2 and Pi, and the volume will remain same. So T2 is equal to gamma Ti. Just show that T2 is equal to gamma Ti by 1 plus P1 by Pi gamma Ti by T1 minus 1. So let's first do mass balance. Mass balance gives us that dm by dt of control volume is equal to m dot I minus m dot t. Here m dot is equal to 0 as it has no exit. Similarly, w dot and q dot is equal to 0. Not mentioned in question. Okay, so this is 0. So this is your first equation. Next we do energy balance. We get du by dt control volume is equal to m dot I h I minus m dot e h. This is again 0 because there is no exit. So is equal to m dot I h I. Your m dot I is equal to dm by dt of control volume. So this gives u2 minus u1 by delta t equal to m2 minus delta t. So this means u2 minus u1 is equal to m2 minus m1 hi. So u2 minus u1 is equal to m2 minus m1 hi. And we know that m1 is equal to T1V by RT1. M2 is equal to final pressure is Pi, V by final temperature is T. So on substituting this, M2 CV T2 is U2. M2 is equal to Pi V by R T2 CV T2 minus M1. T1 V by R T1 T2 T1 is equal to M2 is Ti V by R T2 minus M1 T1 V by R T1. Hi is Cv. First let's cancel all the R's and all the CVs becomes gamma. And then this T2 and this T2 get cancelled, this T1 and this T1. And volume will also get cancelled. This will become Pi minus P1 is equal to Pi by T2 minus T1 by T1 gamma Pi. We have to find T2. So this becomes Pi minus P1 plus P1 by P1 gamma Ti is equal to Pi by T2 gamma Ti is equal to T1 Pi minus P1 plus P1 gamma Ti by T1 is equal to Pi gamma Ti. T2 is equal to T1 Pi gamma by T1 Pi minus T1 plus P1 gamma Ti into gamma Ti T1 Pi. So T1 Pi we divide the numerator and denominator by T1 Pi. This will become 1 by Pi minus T1 by T1 Pi. T1 Pi T1 gamma gamma Ti by 1 plus T1 by Pi gamma Pi by T1 minus this we have shown. Some extension to these questions will be like initially the temperature right here are 0 like vacuum. Then what happens is the P1 is equal to 0, P1 is equal to 0, this implies T2 is equal to gamma T. So this is a very interesting observation. It can be asked sometimes in 1 mark questions as well. So this is T and this is a tank and it is initially at vacuum. Now it is filled such that the pressure becomes same in both this line and the tank. And what is the final temperature? This temperature is equal to gamma of the temperature in the line. It is actually higher than the temperature in the line. Now let's come to the next question. Question number 14. In question number 14, a mass of 15 kg of air in a piston cylinder device is heated from 25 to 77 degrees centigrade by passing current through a resistance heater inside the cylinder. Okay. The pressure inside the cylinder is held constant at 300 kilopascal during the process, and the heat loss of 60 kilojoule occurs. Determine the electric energy supplied. So it is a piston. Piston can move up and down, and P is equal to constant. Okay, mass M air is equal to 15 kg, 25. Initial is equal to 25 degrees centigrade. T final is equal to 77. That's to be plus 2. Okay. And constant, and the pressure is equal to constant is equal to 300 kilopascal. Determine the electric energy supplied and heat loss. Q dot is equal to minus 60 kilojoules. So we have T initial, we have T final. So we have U2 minus U1 is equal to MCV T final minus T initial. Air, that is ideal gas. So we can directly write this formula for an ideal gas. So, and we have 15 into CV of air 0.718. T final minus T initial is 77 minus 25 is 52. So this will give us U2 minus U1. Now, what we need to find, now we'll apply the first law. Applying first law. Electrical energy is a form of work. So here work is happening to two processes. One is by the piston and the other is from the electric. Okay, so your Q dot is equal to Q is equal to U2 minus U1 plus 7. So this is minus 60. We have U2 minus U1, and then work. One is P into V2 minus V1, then work done, so positive, plus the one which you are trying to find. This we know, this we know. So this has to be found first. So what is our V1 and V2? So for a constant pressure process, V2 by V1 is equal to T2 by temperature in Kelvin. Okay. V2 by V1 is equal to, we have T2 by T1, 77 plus 273 by 25 plus 273. Many people will forget to change this into Kelvin. Please take care. In all the governing equations, because we are using ideal gas law. The ideal gas law, the temperature is in Kelvin, so all the temperatures must be converted to Kelvin. So you got the ratio of V2 by V1, but we do not know the values of V2 by V1. For that, you can use the case 1 where M is equal to 15 kg. The PV is equal to MRT. You know, pressure is equal to 300 kilopascal, and the volume V1, M is 15, R for air is 0.27, and temperature is 25 plus 270. So with this you get V1, and with that you get V2 as well. From the ratio, you get V2. So you get ratio P into V2 minus V1. Will give you the work done by the piston. Substituting this in the previous equation, substituting that into this, so you know all the three values, you only need to find it. So next, let's look at the next problem. Air in a rigid tank, air, that is ideal. Gas, rigid tank is given. So, okay. A rigid tank is at 100 kilopascal. T is equal to 100 kilopascal. T is equal to 300 Kelvin. B is equal to 0.75 meter. Now the tank is heated to 400 Kelvin. That is state 2. State 1. T is equal to 400 Kelvin. Okay. Now one side of that tank. Now it is state 3. One side of the tank acts as a piston, letting the air expand slowly at constant temperature to state. T is equal to 400. Constant temperature. This is rigid, means constant volume. So V is equal to 0.75 liter. Temperature. State 3 with the volume of 1.5 meter. So here volume is equal to 1.5 meter. Find the pressures at state 2 and state 3. Find the total work and total heat transfer. So P2 and P3. So for ideal gas, constant volume, governing equation. Constant volume. We can write P2 by P1 is equal to P2 by T1. So P2 is equal to 100. P2 by T1 is 4 by 3. We get this. P2 will get. So now governing equation for constant pressure. Sorry, next one is constant temperature. Right? P1 V1 is equal to P. Constant temperature. So or this for 2 to 3, P3 V3 is equal to P2. Here we do not know this. The V3 we know, V2 we know, P2 we know. So P3 can be found. In the next part of the question, they asked to find the total work and total heat transfer. So for total work, so for 1 to 2, constant volume. 1 to 2 is constant volume. Work is equal to 0. For 2 to 3, constant temperature. So work 2 to 3 is equal to P2 V2 ln P3 by V2. You know P2 V2 V3 and V2. Okay, that we get. So total work will be addition of 1 to 2. And total heat. Case 1, constant volume. So Q1 to 2, case 1 or 1 to 2 process. So Q1 to 2, constant volume, MCVD. You know mass. Okay, we don't know mass. Mass is not given directly. Dt, you know temperatures, both temperature, and CV of air is already known. CV of air is not dt, so mass. How can mass be calculated? PV by RT is equal to M. In state 1, you know pressure 100, and volume is 0.75, R 0.287, temperature. So with this we can get M, and that M we can substitute. So Q1 to 2 and Q2 to 3 is same as W2 to 3 as isothermal closed system, ideal gases. So that can be substituted directly. So we already know this. So Q2 to 3 also. So Q1 to 2 to 3 is equal to Q1 to 2. So we'll get the net heat transfer.